Good morning, grade 9. So this is section 3 of chapter 21. You are going to explain how echoes are made and describe their use in locating objects, to list examples of constructive and destructive interference of sound waves, and explain what resonance is. So our lesson is interaction of the sound. The first thing of the interactions is going to be the reflection. So what is reflection? As you know, it is the bouncing back of a wave after it strikes a barrier. As we know, it is echo. So what is the echo? It's a reflected sound wave. So the strength of a reflected sound wave depends on the reflecting surface. Sound waves reflect best off smooth, hard surfaces, as we know in this figure. In the empty and the smooth, hard walls like this in the gymnasium, sound waves easily reflected off the smooth, hard walls of gymnasium. For this reason, you hear an echo. But in this picture, you can see that here the walls are well designed. Echoes are reduced by soft material that absorb sound waves and by irregular shapes that scatter sound waves, so you don't hear your voice, you can't feel the echo. The other thing of the sound is the echolocation, which means to locate something or know the place of something by phenomena called the echolocation. So here, as we know, the echolocation is the process of using reflecting sound waves to find objects using by animals such as bats. Not only the bats, dolphins, kind of birds, they use the echolocation to hunt food and to find objects. Let's see how the bat works to find its food. First, the bats emit ultrasonic waves as they fly. They produce ultrasonic, which means a sound, a very loud sound. Here, we can't feel it. Now, number 2, when the sound waves strike an object, the waves are reflected back to the bat. The time it takes for the echoes to reach the bat lets the bat know how far away the obstacle is, and then it goes to forward it. The bat can detect an insect flying toward it because of the Doppler effect. As we said before, the Doppler effect means the sound, how it's loud or low. The echo will have a higher frequency than that of the original sound wave. So it uses the ultrasonic sound in order to make echoes, and then when it goes back to it, it can locate where it's exactly. Now, we also, as humans, we use echolocation for many things. We call the electric thing that we use echolocation in, we call it a sonar. So the sonar is a type of electronic echolocation. Look at this figure. These people use the sonar to make ultrasonic sound waves, and then they, when the sound go back as echoes, they can determine if there is a fish here or not by going back, and to determine the distance, how it's far away or something like this. So sonar can also help navigators on ships avoid icebergs also can help oceanographers map the ocean floor, by the same way. Here, another thing that we use as a human, something called ultrasonography. The ultrasonography, it's a medical procedure that uses echoes to see inside the patient's body without doing surgeries. Like, for example, to check the babies inside the mothers, or to check the kidneys and other organs inside the human body. As we can see here, then these electrons goes as a pictures in the television. And ultrasonic waves are less harmful to human tissues than X-rays. The other things of sound interference of sound waves. Now, the interference means happens when two or more waves overlap together. Most of the main way to use this is in orchestras. Let's see this diagram. Okay, the principle is making constructive and destructive waves. Okay, so sound waves form when two speakers producing sound of the same frequency combined by both constructive and destructive. So if you want to make the sound louder, they make it constructive interference. When they want the sound will be softer, then they make destructive interference. I don't want you to get the details from here, just I want you to know the definition and where to use it in orchestras, and the principle of it is constructive and destructive. Like this, okay? You can see that these are constructive, they join together, and the destructive here, as you can see, they delete each other, so the sound will be softer. Now, this is something about the jet planes, okay? The interference and the sound barrier, how they use the destructive and constructive to move, how the jet planes they move. Now look at this figure. I want you to study the figures only here. When a jet plane reaches the speed of sound, the sound wave in front of the jet combines with the constructive interference. Look at this point. As you can see here, the waves are joined together, or okay, to make a large wave or a huge wave. We call it here combined by constructive interference at this point. So this is a constructive interference. When the plane goes in a speed, okay, faster than the sound speed, something called supersonic speed, okay, the sound wave is created spread out behind, so the waves will be behind the plane. Why? Because it's moving in a supersonic speed. So what happened exactly is when the edge of the cone here, something called cone like this, okay, forms. When the edge of the cone, the sound waves combine by constructive interference to produce shock wave, okay, so the plane can get rid of the pressure here and go forward. When you hear the sonic boom, you hear it when when the shock wave reaches you. This we call it a shock wave, okay, the edge. When it reaches you, you hear the sonic boom, not when the plane over or get over the sound speed, okay? Now, here it's about interference and the standing waves. What is a standing wave? Now, when you play a guitar, you look at the strings, okay? You feel that they are not moving, but actually they are moving in a standing wave. A standing wave, it's a pattern of vibration that stimulates a wave that is standing still, okay? So where the string seems to be standing still, waves are interfering destructively, so they are deleting each other, okay? Look at this figure. So let's suppose that these are the strings, okay? Here, the lowest resonant frequency is called fundamental, okay? As we known before. Here, when the higher resonant frequency are called overtones, okay, the first overtone is twice the frequency of the fundamental. So look at these are twice. And then when it's overtone is 3 times the fundamental. The second wave here, overtone, it's 3 times the fundamental, okay? Here, the third, okay, it is 4 times, 1, 2, 3, 4, 4 times the fundamental wave here, like here, okay? So it's not that important to know it, but just I want you to know that standing wave, it's a pattern of vibration that looks like a wave that is standing still, okay? Here, what happens here to make the vibration while they are standing, the frequencies at which standing waves are made are called resonant frequencies, So the resonance, it is happening when an object vibrating at or near a resonant frequency of a second object causes the second object to vibrate. Which means when you just move one string, the other strings will start to move. Or when you want to make this fork, the sound fork, if you want it to move, just put it beside something is already vibrating, so it will start to vibrate. So without touching it, without pushing it, it will start to vibrate. Why? Because a phenomena called resonance. Okay, the resonance here, it happens because of a vibrating object beside it. So it will push the air toward it and then make it vibrate without moving it. Exactly this happens in the guitar. Why the guitar from the inside, the body of the guitar, it's empty? Because when you make something here, guitar, the string, when you move it, you are making a standing still. Okay, so when you make standing waves from inside the body of the guitar, sound now it's amplified. So this hollow body, when the string vibrates, sound waves enters the body of the guitar. Standing waves form inside the body of the guitar, and sound is. So you are pushing the strings. Okay. So inside the body, it's hollow. It is air. So you are making the air to vibrate, and then it will go back to make the other strings vibrate. Okay, and this make the music or the tune that